Recording. Okay, so welcome back, and we are still in the middle of discussing this chapter 3, which is about various complexity measure. It's about Rademacher complexity, and then growth function and VC dimension. So we are not going to cover the last part in the textbook, which is about the lower bound. I mean, my problem is I couldn't really follow it. I mean, maybe there are some typos, and the combination of typos and my lack of understanding, it just make it impossible for me to understand what's going on. So I'm not going to cover that part, but we will cover up to the VC dimension. So today we'll finish off this chapter 3 and then just solve some exercise. So then the particular part we're going to cover today is a VC dimension. And here's a quick reminder about what we discussed in the last time. And then the goal of talking about VC dimension and so on is to have some complexity measure for our hypothesis class. We have a hypothesis class, and we want to have some complexity measure. And then that complexity measure allows us to have a general bound on the generalization error. In other words, it becomes the main tools that we can use to derive, in a sense, guarantee for our induction, which is happening inherently by learning algorithms. And then we discussed about Rademacher complexity before. There were empirical Rademacher complexity as well as the Rademacher complexity for our hypothesis class. And this is the most informative because the Rademacher complexity depends on the distributions over the input or input-output pairs. So actually over the inputs. So it really takes some extra bit of information, which is a distribution. On the other hand, it's a bit more difficult to compute. So we consider the growth function, which doesn't depending on the, I think some of you turned on the speaker. So, okay, now it should be okay. Okay, and then we talk about growth function, which is independent of the distribution. So it's less informative, but the growth function is easier to deal with. I mean, you can see it in the exercise that we're going to do today. And then the last things that we talked about is a VC dimension. That is more abstract than the growth function. But it's easier to deal with. Okay, so what was the VC dimension? The VC dimension, intuitively, is the size of A maximum. So it's the largest finite subset of inputs such that any labeling of the elements in the subset subset X, let's call it X0, and X0 can be correctly classified by correctly, I mean with error 0. By some hypothesis H in our hypothesis set. So whatever label you give, I mean, we can in a sense we can get it right with 0 error by choosing appropriate hypothesis. Okay, and the maximum or largest, if the the largest finite subset doesn't exist, which means that for any n there is always such a subset, then the VC dimension is infinite. More formally, VC dimension is defined in terms of a growth function. And then the growth function was it was the primum of m such that growth function has the largest value. Okay. So 2 to the n. So in this context, we are always thinking about our hypothesis is a mapping from input to -1 and +1. And then this growth function is defined by the maximum over inputs size m such that cardinality each of xn. So in a sense, the labeling that we can give by using some hypothesis is maximized. Okay, so that's the definition of the growth function. And then we look at the VC the maximum finite subsets, which can be completely classified. For which any labeling can be classified correctly. This is we said introduced a concept called the shattered to talk about such a subset, and then VC dimension can also be phrased as the size of the largest shattered finite subsets of the input. Okay, so then we looked at VC dimension of a few examples. And what we're gonna do, reminder and overview. So we will use VC dimension to get a generalization bound. So specific results, so generalization bound will have the sum form that we have talked about so far. It is, say, for probability over sample of size m, then we have a guarantee, uniform guarantee for every hypothesis, and the uniform guarantee said the risk, the generalization error is bounded by empirical error over S, but we have to put some slag to get a guarantee. That's one part of the slag is something that is related to the complexity of our hypothesis class. And the other is really coming from the use of concentration bound, which is 2m, so 1 over delta. And that was greater than 1 over delta. And then the Rademacher complexity, what's coming here was Rademacher complexity of the hypothesis H. And then when we talk about growth function, we show that this Rademacher complexity is bounded by growth functions, which is m over, I think it's 2 log of growth function. And then what we're going to show today is that this growth function is also going to be bounded by bounded by the quantity that I'm going to show you, E m over d, like this. So this is the key result that we were going to show today. And actually the key result is inequality between growth function and this quantity. And by plugging this upper bound, which holds regardless of any distribution, and we will obtain a generalization bound. So for all H, its risk is bounded by empirical risk plus this quantity, which has nothing to do with distribution, plus some extra bits, which is coming from the concentration bound. The probability is always great, is very large. So 1 minus delta means very large. So that's what we're gonna do. So this is the number. Right. This is corollary 3.18. That's what we're gonna show. and the version of the upper bound with this the VC dimension is going to be the corollary 3.19. So that is the final outcome. Okay, so that's what we'll do. And let's just start. Here's just some generalization bound. With VC dimension. So that's what we talk about next. Okay, so to talk about generalization bound, let's get some more intuition about, so one thing that we're gonna show, which is the corollary 3.18. So that is the key result, okay? And that enabled, once we know corollary 3.18, we get a generalization bound. What is corollary 3.18? The corollary 3.18 said if VC dimension of our hypothesis class is equal to D, so then we can bounce the growth function. H M is going to be bounded by B M over D and D. So that is the result. Now, I mean, if you look at this result, just say, okay, there are a bunch of numbers. What does it really say? Qualitative. I mean, you may not really get the qualitative information from this bound. But what this bound really tells us is, in some sense, quite interesting. I mean, so think about this growth function. So this growth function is bounded, its possible maximum value is 2 to the n. This is growing exponentially. And by the definition of the VC dimension, up to the VC dimension D, so if this is value of M, I mean, this is the value of this growth function and so on, this 2 to the M function is growing like exponentially, like this. But then if the VC dimension is D, then the growth function follows this exponential function. So this is 2 to the M. It grows like an exponential function up to D. Okay, but this bound, I think this bound is for actually. Okay, there is some condition which I forgot. Or and what this bound says, after D, up to D, growth function grows exponentially, but after D, it grows polynomial. If you look at the input is M, and then it's a polynomial function. Maybe D is a high degree, but it's a polynomial function instead of exponential function. So this is the corollary 3.18 really tells us up to D it grows exponentially, this growth function, but after D it grows polynomial. So it's a much it grows much slower than the exponential function. So this is I. So in some sense, there is a kind of qualitative transition that's happening in the VC dimension point. And the key message of the generalization bounds and this VC dimension theory is saying this, in a sense, critical, I mean, the kind of phase transition point capture a lot of information about this growth function, and it can be used to derive an upper bound. I mean, to derive generalization, meaningful generalization bound. So now the question becomes how we can prove this theorem. So to prove this theorem, we're going to use something called the Source Lemma. And we will prove the Source Lemma later. But let me mention this lemma first. Theorem. Sorry, I will close the window. Source Lemma is Lemma 3.7. The theorem 3.17 in the textbook, it says the following. If the visit dimension is equal to D in the same, under the same assumption, then we have I, the growth function, by I is equal to 0 to D, and I for M. So instead of this condition above, we here in the below, we don't have any this condition. This is called Source Lemma. So as I said, we're gonna use this, prove this lemma, but let's hold it for a while, and then say, assume this Source Lemma is true. And under this assumption, let's try to prove the corollary 3.19. And how we can do this. And the proof is actually quite, I mean, it's a calculation, but it's not so hard. And so also, if you look at the proof, you will see that where this strange number, which is this exponential, is really coming from. That's because we are approximating polynomial by this exponential, by an exponential function. So how you do it? So we just do the calculation. We have a growth function m, and by the Source Lemma, that is less than equal to I is equal to 0 to D m. So our assumption at the moment is m is greater than equal to D. Then what we do, so we will consider the quantity m over D. This is always greater than equal to 1. And we're going to multiply to these things. So that's equal to 0 to D. So we are losing something, but instead, in return, we make things a bit simpler. So m over D minus I. And then we also approximate it by making this bounds larger. So I mean, D is smaller than M. So if we increase, we can, by increasing D to M, we can make all numbers larger. That's equal to 0 to M, which M over D minus I. Then we take out, I mean, this is D part and leave minus I part. So then D summation 0 to M and M over D minus I. So, I mean, if you reach so far, then you can kind of see that, okay, we are almost there. I mean, if you compare what we have here, and then the quantity that we are really aiming at, that's pretty similar, except that we have an e to the d. So what this means is, if we can show this summation part is bounded by e to the d, then we are done. And that's also not very difficult to do, because I mean, all that is additional kind of approximation or loosening of the bound is there to make the formula have a nice form, and this will actually have a very nice form. So this one, same as m over d, summation I is equal to 0 to m, which is I, d over m over I. But what I just showed in the parenthesis, this part is the same as 1 plus d over m to the m. So if you expand this polynomial, then I mean, what we get is the one above. I mean, the ith term really coming from choosing in this multiplication of m vectors. There are I way of choosing as the second term, and that will give the term with the ith power here. So that's possibility is captured by this m choose I. So that's what we get here. But then finally we approximate this quantity by exponential function, because 1 plus x, I mean, this is used many times, exponential x. So if we bound this, that's going to be e to the m times m over d. So that is same as e of d. If you put all these things together, we get an upper bound and d. That gives the what the lemma claims. So I know it's, you know, in my experience, I mean, when you look at numbers like this, it was very difficult to either remember or you just make sense out of this. But once you get used to the proof, I mean, I'm sure, I think you may get some intuition, like whenever you look at numbers like e here, number like e here, you may imagine, so in your mind, you may kind of either remember or guess some inequality like this is used somewhere in the proof. Okay. And then right. Okay, so that's the proof of the corollary 3.18. The proof is calculation, but it's really kind of, it's just per calculation that exploits the Source Lemma. And then once the corollary 3.18 is proved, then we can get a generalization bound that I showed you in the previous slide. So then now the question becomes how we can prove lemma 3.17. In some sense, that's the key part of approximating the growth function in terms of basic dimension. Okay, so this result is the key of the theory that we are developing so far. And how can we do it? And the proof is a bit more involved. There's a theorem 3.17 again. 17. And the basic dimension of each is equal to d. Then we have bound on the growth function. Is 0 to d. That's true for all. So the question is how we can prove this. So then the proof uses induction on d plus n. Okay, what are the base cases? So we consider two base cases. The first base case is d is equal to 1. Not 1. D is equal to so d is equal to 0. That's a one base case. And the other base case is when m is equal to 1. Okay, that's we're gonna consider them separately. So if d is equal to wholes, for very simple reasons. So if d is equal to 0, then what happens is that this growth function becomes really simple. And why is that? If d is equal to 0, that means our hypothesis class should have only one element. Okay. Otherwise, if we have at least two elements, two functions in our hypothesis set, then there must exist some input for which our hypothesis set, one hypothesis map it to plus, the other hypothesis will map it to to minus. Okay. So if the hypothesis is because if our hypothesis is that it's greater than or equal to 2, then with dimension d has to be at least 1. So there is a singleton set will be shattered. Okay. So this is equal to 1. If our hypothesis set is equal to 1, then the growth function of m will always be equal to 1. So that's going to be bounded by I 0 to d, in this case 0 to m over I. So choosing nothing, which is m over 0, that is equal to 1. So that case is true, and then the key observation in this case is with dimension 0 means there's only one hypothesis. Then what are the other base case? The other base case is it is greater than 0, but m is equal to 1. But if m is equal to 1, then the growth function will be m most 2. Because this is bound by 2 to the m, it's m most 2. But then what we do know is, because d is greater than 0, this is summing from 0 to d, m to I, m is at least 1, and then d is great, also at least 1. And this quantity, this inequality is true because of this assumption. So that also shows the inequality that we want to prove is also true here. This is also true here. So there are two basic cases are okay. So now how to do the inductive case. So to show the inductive case, we will introduce one notation. So that notation is for any finite subsets, the finite subset of x. So actually, for finite subset of x, we're gonna write it h restricted to s to mean the following, which is the function whose domain is restricted to s. So this is going to be a mapping from to -1 and +1. And h is in our hypothesis set. So another way to look at it is if s is x1 up to xm, so they are all different. If that's the case, the h restricts to s. So let me write it differently. I think explain this slightly differently. So let's call it S to be a sequence of size m. So then, for any sub m, we write it as h of restricted S. So because it's a sequence, we have x1, xm. H restricted to S means so just a vector of size m, which we obtain by applying h to every element for some h in h. Okay. So so if you do so, okay. So if we do so, then we can think about the following. A, can think about the, if we pick, so we pick M to show this inequality, and also pick S such that, which is a sequence of size M, such that the pi h of M is equal to, pi h of M is equal to H restricted S. Let me take it back. I think let me just use the original one. That's a bit easier. Sorry about keep changing. Subset and use this different notation. I think in the textbook they keep confusing sequence which allow the duplication and subset which doesn't allow duplication. That is okay because of some concept something, but it wasn't very clear about this, so that's why I changing things. Okay, so this restricting x0 from 2 minus 1 plus 1 of h. So take any hypothesis and we are restricting that hypothesis to a subset x0. So that's what we are doing above here. And then for the growth function, because it's defined over the maximum over the sequence, we pick some sequence of size m. And then what we are doing here is that there exists some sequence of size m such that this this growth function is exactly cardinality of the S is x1 to xm. So x1, x2, so on, each of xm such that h. So that because it's a maximum, it's defined this way. But one thing you can notice immediately is if there is some S like this, because it's a sequence, there may be a duplication. So some element, for instance, x1 and xm may be the same. But then, I mean, if x1 and xm are the same, they will receive exactly the same label. So the maximum can also be achieved by a sequence where there are no duplication. Okay. Such that this quantity is true, and then second, xi different from xj. Okay. Or I is different from j. So what we're gonna do? So we will. So what we were gonna do is that we will let. So we will consider a few sets. The first set is x is 0, which will be the which will be the set of S. So in other words, this is one. I mean, maybe if you are mathematicians, you may be a bit less strict about whether we are dealing with sequence or dealing with a set. But for the computer scientists who work with formal verification, there's just some distinction between the two. And then we also, if we let x1 will be the same as x0, except we are removing the last element. So this X is capital. So these guys are capital letters. Okay. So while we are doing this, I mean, okay, the first things that we can notice is that now pi of h, let's use space there. So the first thing we can notice is pi of h and m, the same as the cardinality of h restricted to x0. I mean, because with all these because the small x1 up to xm are all different, yeah. Small x1 and xm are all different, yeah. But I mean, each of these vector correspond to the restriction of h with respect to x1, small x2 of the small xm. Okay, and different vector means the restrictions are different. So these vectors are in one-to-one correspondence with this restriction that I just defined there. So it's the same. And now here are some important things. So we're gonna define so we will consider h restricts to x1. So now there are two players. One is h restricted to x0, h restricted to x1. Then we're gonna define some subset of h restricted to x1. We will write it as a h prime. And that consists of elements in this restriction, but it satisfies the following property that exists. Restriction over the larger set, this x0, such that if you restrict h1 to x1, so in other words, if we get rid of this last element, okay, this last element of xm, so then in this same as h2 x1, and that's same as h. Okay, so that's the first property. The second property is that now, if you look at the behavior of h1 on this removed element xm, they are different. In one case, it's a +1. In the other case, is -1. So h prime that we just defined is a subset of the h restricted to x1. Okay, so why we are doing this? So we are doing this because we're gonna want to do some induction using h of x1 and h prime. And then the inductions, let us prove this theorem. And the reason is what I'm gonna just tell you. So some important property is that h of x is 0, which means the restriction over the larger set, cardinality is same as h of x1 plus h prime. So this is the one important fact. So this is an important fact that enables us to the inductive proof. Now the question is why this is so, and let me tell you this. And the reason is, now, if you look at how this h of x0 and h of x1 is defined, I mean, h restricted to x1 in this guy is defined by taking some elements in the larger set, I mean, the function defined over the larger set and restricting its domain. So we have a function in the picture, we have a function that's defined on the larger set x0 to x1 plus 1 each. Then we restricted this so that we got rid of these elements. And we only look at x1 and then obtain function that behave with respect to x1. If you do so, then maybe initially we have a function h1 and h2. They are different, but after this restriction, they may become the same. Okay? So the one thing that you can immediately see is that cardinality over x1 is smaller than or equal to cardinality over x0. That's one thing, immediate things that you can know. But we want to have, we want to see how much this difference, how much is this difference, and that difference is exactly captured by the cardinality of the second graph. So when two things are, how much two things are differ, these two things are differ whenever there is a h1 and h2, they are originally different, but they become the same after the restriction. And the h prime is really picking out the something like this restricted function, for which we can have two different original functions like h1 and h2. Okay. So this h prime, say that's just something in h restricted to x1, but it can come from two different functions, h1 and h2. They map this xm, the kicked out inputs, to two different values. Okay. So that's why this inequality is true. So that's one important thing in this construction. And the other important bit this construction is now we have this h prime, h restricted x1, h restricted x0. They are all, in some sense, hypothesis sets. Okay, so we can talk about this VC dimension. Then one immediate things that we can talk about is the VC dimension of h restricted to x1. That is smaller than or equal to VC dimension of h, original h, which is equal to d. And the same thing happens. H prime is less than or equal to VC dimension h. This is always the case whenever you have a hypothesis set. If you restrict it, you obtain another hypothesis set by restricting the domain of the inputs. The VC dimension always get reduced. Okay, so that's all. This is always true coming from the definition of VC dimension. But one important bit is that actually for the second, for this second, we can do better. Instead of this upper bound, we can actually have a better upper bound, which is minus, and which is a d minus 1. So we can have, this better upper bound. And why that is the case? That's because if some subset of y, ask y, That's because if we have some subset, x1 prime, which is a subset of x0, if x1 prime is shattered by h prime, if that's the case, then x1 prime union xm. Xm is not, I think this is not 0. So this xm is not in x1. So this is small x1, capital X1 prime and small xm. And that is all is shattered by h. So by h restricted to x0. So that's because the way we define the h prime, I mean, for any functions, the h, we can always find its extension, h1 and h2, which will assign different labels for xm. And that property ensures if x1 prime is shattered by h prime, some prime is shattered by x prime, and extending it with xm is going to be shattered by h restricted to x0. Okay, but this h, which means, this visit dimension of h prime is less than equal to visit dimension of h restricted to x0 minus 1, but visit dimension of h restricted to x0 is smaller than equal to visit dimension of h minus 1. So that's we have d minus 1. Okay. So that's what we can have. So we need to create some space. There's this. Right. So now from this, we can now complete the proof. Now how to complete the proof? And we start with pi, the growth function of m. Now by this property that we proved, same as cardinality of h is 0. And then that's the same as cardinality of x1 plus h prime. But because now the h of x1 restricted to x1 and h prime, they are defined over inputs of size n minus 1. So if we take a growth function for all the inputs, that's exactly the same as this cardinality. So that's the same as growth function over x1. And this equality happens because n minus 1 is size of the input, which is the size of x1. Same thing. Right? This is n minus 1. And now we can use the induction hypothesis by induction because the m is reduced, and then visit dimension of each of them is also either d or reduced. So if we use the induction hypothesis, then the first guy is going to be bounded I is equal to 0 to d n minus 1 choose I. And second one is going to be bounded by I is equal to 0 to d minus 1 minus 1 choose I. Chain create some more space. So then now we can rewrite the second term by doing like this. To raise it up to d, but then subtract I minus 1. So choosing something minus one element, something is equal to 0. So we can always do it this way. Then once we do this change, and that is same as summation I is equal to 0 to d, n minus 1 choose I plus n minus 1 choose I minus 1. But this is the same as the integer. And the last equality, maybe you remember something that you learned a long time ago, perhaps in high school. This equality comes from the fact that now if you want to choose I elements from m elements, you can, there are two possibilities. The last element, the xm, will be chosen. So then you need to choose I minus 1 element from the first m minus 1 element. So that's, this is second quantity. Or the last element is not included in your subset of size m. So then you have to choose I element from the m minus 1 elements. Okay. So this equality is true, and that's why we have this proof of the Source Lemma is hold. Does hold. Okay. Now taking a step back, so what we really did, we do the induction in the proof. So we prove by inductions, and base case is, it's just case analysis and simple check. Inductive case, that it required some key idea. The key idea was considering the restrictions of with this restriction h restricts x0 and noticing that the growth function can be expressed like this, and then in a sense kind of rephrasing the h restriction to x0 in terms of two subsets. Okay, and then note that this second subset has its VC dimension is bounded by d minus 1. So once you have this much, so this equality in this case, and then this equality and the third observation, and by putting these observations and applying the induction hypothesis, the conclusion part. And in some sense, the key idea of the construction is really considering something like this h prime. Okay, so that's the whole part, completion of our proof. So now where we are. So I'll just write the corollary, the final conclusion again. 3.19. Yeah, so this corollary said the PC dimension H is equal to D. So then for any delta, for any distribution D over input out pairs, so we have probability N of every hypothesis risk is bounded by empirical risk, bounded by some quantity with high probability. And but the quantity, the first quantity talk about the complexity measure 2n. So first quantity talks about complexity measure of the basic dimension, which is to move things around, becomes like this, and d dn divided by d plus un log 1/that. Okay, so that's the final conclusion. One thing you can notice is if, the t appears twice in this formula. So d appears once here and another here, but the vector that's outside of log has a more impact. So if the VC dimension is low, in other words, our hypothesis set is simpler, then the upper bound, we get a tighter upper bound. Okay, so that's the end of the theory. Now let us get kind of to some exercise, practice a little bit and try to digest what's really happening by solving some exercise. So the one exercise I want to try. So it's the one on the exercise 3.24. So what that exercise is say that we have a hypothesis set A. It's to -1 and +1. And another hypothesis set to -1 and +1. And explicit dimension of the A is D of A. Explicit dimension of B is D of B. And now what we're gonna do, we will form a new hypothesis set by taking the union. The first question is show growth function of the union hypothesis set is bounded by growth function of A plus growth function of B. So that's the first exercise. The second exercise asks you to prove the following. So show if I phrase it more difficult way, show that this dimension of C is bounded by, is upper bounded by this dimension of A with the dimension of B +1. So that's the second exercise. And then solving the second exercise, we can do it by using the first exercise. So showing the upper bound of VC dimension really boils down to showing, so this is the second part. Second part maybe look a bit difficult, but actually it's not. So proving this is same as showing the growth function of C with dA plus dB is 2. It is strictly smaller than 2 to the dA plus. If you prove this, then that implies this upper bound. Okay. Now, to prove this, you can use Source Lemma. So, quick reminder here, what Source Lemma tells us. Source Lemma tells us that the hypothesis set M with this dimension so if you use what you can prove with A together with what I just explained to you, then you can prove to B. But the conclusion is actually quite interesting. If you combine two hypotheses set, its VC dimension is increased by Just addition of two set plus one and at most. Okay, I will give you 3 minutes to solve this question. Okay, so here's the solution for this exercise for A. So how to prove this? If you just write down this definition. C of M was the maximum over the sequence x1 to xm input, such that it's a cardinality. So this maximum of the set obtained by applying any hypothesis to the vector is going to be maximized. So let's write this as an vector notation and then write supporting as h of x. But then this C is obtained by set A union B. No. So the up to the VC dimension, up to the VC dimension, this is holds with equality. And then if it grows right over the VC dimensions, then it starts to deviate. So here, so the up to VC dimension, the growth function has a maximum value, which is 2 to the m. And then when we go right over the VC dimension, there, I mean, they start to deviate, this exponential function and then growth function deviate. So here, if you, because we are in this, we are using this less than equal, so that's why we have this number. 대답이 됐나요? Okay, thank you. So there we have something like this. So it's a B. And we just and a maximum of this cardinality is going to be bounded by x bar over h bar, where h is from A plus h bar, h is from B. But then if we distribute maximum, that gets larger. So max bar h over x bar h in A plus max bar h B. Then what we get, and the first summand is exactly the growth function m over m and the A, and then the second is the growth functions of B applied to m. That's exactly the bound that we have here. Okay. So then how we can solve the next? I think I have to erase. And then the solution, and then by definition. So that's what how we put A. For B, now we use A, so we plug in this number, dA plus dB is 2. And by the what we proved in A, that's A, dA plus dB 2, and B, dA plus B plus 2. Now we use the Source Lemma, and Source Lemma say the first summand is going to be bounded I is equal to 0 to dA, where dA plus dB plus 2 choose I. And then the second Source Lemma say that from 0 to dB and dA dB plus 2 choose I. The one thing that we can immediately do, I mean, choosing I elements from dA plus dB plus 2 is the same as choosing dA plus dB plus 2 minus I. Then for this entire term, now becomes the same as adding everything from up to dA plus dB plus 2, where start with dA plus 2. If we pick the largest case, I mean dB, what we get is with dB, we have a dA plus 2, so that's why we have this number. And then if we pick the smallest, which is I is equal to 0, Then we have dA plus dB plus 2, so that's why this upper bound, and that's a dA plus dB plus 2, which is I. Now, if you look at what we obtained, and what we obtained is this term plus this term, and that's very much like, so that's very much like summing I from 0 to A plus dB plus 2 plus 2, sorry. Except the one is kicked out. The one thing that's kicked out is when I is equal to dA plus 1. I is equal to dA plus 1. That's not counted. But I mean, this first term that we get, I mean, that's the same as this part is the same as to the, it's counting all the past, I mean the number of all the subsets, so it's dA plus 2. And the quantity that we are subtracting, that is greater than 0, so that implies the whole thing is dA. And so that's how, I mean, that's exactly what we are trying to prove. And so if you do so, then we can solve this exercise. And I think we have 1 more minute. So then let me mention one exercise, and then so some more exercises will appear as a homework, which I hope I can give to you at the end of this weekend. And then there are some interesting exercises that you can try. The exercise 3.7. I mean, it's not very difficult, but if you try it, then you can get some more insight about the Rademacher complexity. In particular, this exercise say if H, I mean, the key message of this exercise is sometimes the generic upper bound gives you something better than what you would get by doing some calculations. So, but then the one key intuitions or key insight in this exercise is that suppose we have a function, the hypothesis set is very, very simple. So we have only 2 functions. One is returning every +1 all the time, and the other function is returning -1 all the time. So in that case, suppose we have to compute the empirical Rademacher complexity, then we compute this. 1/n, and summation is 1 to n. So then in this specific case, actually what appears inside it becomes quite much, I mean, it's not difficult at all, but extremely useful. So in this case, it becomes like this. And this insight can be used to prove, I mean, the solve the exercise 3.7 and some other exercise where something similar happens. Okay, so that's one. Give me 1 more minute, then I will tell you one other things. Also, try to solve exercise 3.25. Doesn't require like a lot of calculation. It just requires some idea, which is if you have the hypothesis is set. Now you pick one hypothesis H, and then you are doing essentially exclusive OR. So forming new hypothesis H prime, which is H mean for H prime is in H. So what this notation means is prime is going to be +1 if they are different. So this is really coming from like symmetric difference or exclusive OR. If they are the same, different, and like an exclusive OR is going to be -1. So that's the new hypothesis set. Then the exercise asks you to prove which dimension of H, same as this dimension H prime. And proving this is not hard at all, but it requires a little bit of thinking. It's quite easy, but it requires a little bit of thinking. Okay, so that's it for today. And I'm gonna stay here for about 5 more minutes. So if you have any questions, you can ask me.